Hello there. So today we're going to learn fundamentals of computing weeks 6, 7 and 8. So week 6 is already covered in week 5, but uh, so it's essentially only 7 and 8. I just like to keep everything in order, so that's why I put this. So today we are going to mainly learn all about assembly, how the language works. We're going to learn about instructions, and we're going to learn about uh, interrupts, so on and so forth. Then we are going to learn about the hardware software interface, right? So here we will learn all about the BIOS, which is basic input output system. We will also learn about operating system types. Uh, we will learn about device drivers, how they work. Uh, we will learn about computer system components, and I believe those are the main things. And under computer system components, we will be learning a bit more detailed. So let us begin by talking about assembly. So buckle up because today is quite the long lecture or video because we have a lot to cover. So let's start off by assembly. Now I'm going to link a specific video from other people. I believe his channel's name is M by X, where they explain assembly in a really nice manner. There's also how registers work from another channel called the Computer Science Lessons. They also explain very well. I will link both of these videos down below, which is very helpful. But I'm going to quickly go through what assembly language is. So assembly language is like a low level programming language. It it talks directly with the computer. So it is the simplest of all languages, and it talks directly to computers and it talks directly to the registers, right? So using assembly, we can be very precise, okay? And if we optimize it very well, we can get very high performance. But the problem is not everyone can master assembly, and it's very tedious to go through assembly. You'll understand why. So assembly uses hex mainly, and it has a few what do I say, a few simple instructions. So before we talk about all that, we need to talk about registers. So as we studied previously, there are general registers, there's special registers, there is status or flags, and finally there is segment. So the general registers has an accumulator AX, base register BX, count register, and a database register. Special registers have something known as stack pointer, base pointer, uh, stack pointer, base pointer, source index, destination index, and last but not least, instruction pointer. So status flags have something called carry flag, zero flag, uh, parity flag, auxiliary flag, and some more. And segment has code segment, data segment is data segment, uh, stack segment, and extra segment. Now, these are the main registers that we use, and essentially assembly does is we can move bits of data from each register and we do it manually. So that's what the main point of assembly is. So let's talk about different assembly languages, different assembly instructions of sort, functions. The first is move, MOV, where if I say move AX, comma 5. So the way we usually read commands is we say the command move to AX the value of 5, or move to AX the value in uh, another register. Because if I have move AX BX, so move to AX the value inside BX, right? So this is move. Then we have add, where I can say add to AX the value of 5, or I can add the value add to AX the value in BX. Similarly, we have subtraction, we have multiplication, and we have division. And along with that, we have jump, we have loop, we have compare, and jump has like two parts essentially. Jump, I believe something is called jump exception or jump not exception, but this is essentially two different ways of jump where it specifies when to jump. And finally, we have interrupt. So we will be talking about interrupt a lot more in detail, but interrupts are essentially say pause the program, execute something else, and then recontinue the program, right? So usually assembly starts with org 100h, where it essentially says start at 100h. So int 21h, where we can tell to pause the program and do whatever this number has. So here are a few. So if we have 01h, that means to read a character from the keyboard. If we have 2h, we have display a character. If we have 9h, we have display a string, and 4ch means terminate the program, right? So we will talk about interrupt a bit later while we talk about computer subsystems. So with all this out of the way, let us now begin by talking about components of a processor. So a processor, or a central processing unit, has, as usual, three main parts. It has an input and output. Uh, it has a CPU. By the way, this is actually not a CPU, it's actually a processor, parts of the processor. Okay, anyways, it has an input output, a CPU, and a memory unit. And a CPU has three main parts. It has a control unit, arithmetic logical unit, and it has registers. So what are registers? Well, registers are very small memory that is used to access data really fast. That is the simplest form of explanation for registers. So let's look at what each and every single one of these parts does. So a control unit is used to fetch, decode, and execute commands from memory unit. ALU does arithmetic and logical functions, and registers are used to store data temporarily for quick access. Okay, so it'll fetch, so the CU control unit fetch, decode, execute command from the MBU, and it'll always also send a flag. It'll either send a carry flag to symbolize, okay, we need to carry a value from another point to another. It'll send a zero flag. I don't know when it'll send, but it'll usually send out a flag, right? So let's talk about the ALU a bit more. The ALU, right, it does all the arithmetic and logical calculation, the computational operations inside of a computer or the processor. So we usually say the data, right? So if I have data, that is the usual term for whatever it's working on. But here we use the word operand. And operator is the function we're gonna execute. So it may be plus, minus, subdivision, or multiplication. Anyway, is the operator. And finally, ALU is in charge of some control signals. So let's say you want to add 9 plus 2. You will get 11. So since you have to carry one out to another value, it will send a carry flag out depending on what it needs to do, right? So essentially, it will always explain the result. And finally, we have registers that store data temporarily for quick access. Uh, it will usually hold these operands. Holding these operands is the point of registers. And so we talked about registers, and there are so many types. There's 8-bit, there's 16, there's 32, and there's 64-bit registers. Okay, so there's a very important thing. Assembly language differs from all these different processors, right? x86, ARM, RIC, SCV, all these different processors has different assembly languages and how they connect. So assembly varies from processor to processor. So again, that is another one of the drawbacks of using assembly. It is not universal. So we talked about move, we talked about add, subtract, all that. So how do we use that? So before we do that, we have to learn about addressing modes. What is addressing? Well, there are a few addressing modes. Immediate addressing mode, and then there is direct register, direct addressing mode. There is indirect addressing mode. There is register addressing mode. and there is indexed addressing mode. Now, what are these addressing modes? Well, these are different ways on how you can write uh, code in assembly essentially. So a good example for immediate is if we're gonna move into AX the value of 5, that is directly, not directly, immediately you're putting it, right? So we are moving the data or the operand in the instruction itself. Okay. So next we have direct addressing mode, where we point out to the place where we need to move the address of the register. Okay. So it's like this. And I'm going to link the video that explains this very beautifully. But essentially, what we do is this says, okay, in this address, there is a data, access it and put it to AX accumulator. And indirect addressing mode is one step further than this, where what we do is we say, okay, go to this location, go to this location, there will be a location there, go there and take that value and put it into AX. Register addressing mode is already talked about. We can do something like this, where take the value inside Rx and put into AX. So the way you think about this, the function into where we want it to happen, from where or what, right? So remember this way of seeing this. Again, I believe MYX explained this really nicely. I will link their video down below. Finally, we have indexed addressing mode. It is essentially saying move to this direction, the data in here or address in here plus 4, right? So this is what somehow acts like a jump. So it will usually check if there are boxes like this. If I'm saying this is R2, then it's going to add 4 and it will always put out this box. So these are the addressing modes when it comes to uh, assembly. So immediate, we are putting the operand directly in the instruction. Direct addressing mode, we will directly write the address so that we can extract the data in the address. Indirect addressing mode goes into the place where the address is held, goes again into the address and extracts the data and puts it into where it wants. Register addressing mode takes the data from one register, puts it into another. Index addressing mode takes the address of the specific register, adds a specific constant to it, goes to that address, takes the data from that address and puts it into R1. So these are addressing modes. Now let us talk about processor instructions or assembly instructions. So again, like we discussed, we have the OG move, we have the arithmetic ones, add, sum, multiply, divide. We have logical operations and or not. We also have some more. We have load, we have store, we have branching or jump, where we go BR, we have jump, and we have loop. As I said, jump has two, JE and JNE. Then we have something of a null, which is no operation instructions. And finally, we have interrupts. These are so many processor instructions. So let us first talk about interrupts. So how do these interrupts work? What are interrupts? So essentially what it happens is, we will learn this later, but a processor has two ways of checking things or doing things. For instance, one method is called polling method, where the processor uh, regularly checks on something and sees whether it needs something done, and then it executes it, and then it keeps on looping. The problem with this is highly inefficient. So what programmers or the creators of computers have used is the interrupt function. The processor keeps on working as normal, but let's say a device needs something done. It'll interrupt the machine. The machine pauses the other stuff, deals with this issue, and then it continues on, and the interrupt is solved. That is what the interrupt is. And the interrupt is not essentially a bad thing. It sounds like interruption, not good, but it's essentially just a way of saying, okay, it pauses everything else, deals with whatever it has interrupted by, and then it continues on. Interrupt is way more efficient and time consuming, and again, efficient when saving energy when compared to polling. So there's three types of interrupts. There's the hardware interrupt. So if I type a letter, if I type a key or something, the key will be going into the PC, sorry, processor. The processor then sees, okay, I have gotten an input, I need to accept, put it out somewhere, and then it puts it out somewhere. Similarly, there's software interrupt, and then there's something called traps, where it's essentially meant to be like, okay, this code will loop infinitely and will may cause issues. Hence, I must interrupt the program to tell it, okay, this program will not work, so on and so forth. Right? So, all of these happen towards the operating system. The operating system is the one who deals with all these interrupts. Right? So, let us talk about the input output, because it's another important part. Input output operations. So as you know, input output operations is basically to transfer data from input output devices to processor. So there's many kinds of this. So first off, there's the input output port, where each device has its own unique port number. Each device has a unique port number, and which each unique port is used to transmit or receive data. So examples for those are HDMI port, VGA port, all those ports. Next, we have memory mapped input output. Essentially, the processor has the input output already on it. So input output devices are mapped directly into regular memory address. Now, a good example for this is you're gonna need an input output port to connect a mouse to your laptop. But if your laptop has a keyboard already, there is no use in creating a specific port for your keyboard, right? So it's best if to your laptop, you have already memory mapped that keyboard to it, to the processor itself, right? So that you can save time without checking for the port. So those are two different physical aspects. Next, we have programmed input output, and we have interrupt driven input output. So the program input output is the processor will do all the work. So in a group project, if one guy does every single thing, you know how bad he feels. He will be overworked, he will be tired, he will be stressed. So program input output means the processor does everything, right? So everything as in it transmits data by itself uh, to input output devices. So it is responsible for everything. Whereas interrupt driven data is like, the team leader is doing something, but the others come and ask him, hey, can you help me with this? And the team leader drops his work temporarily, helps the team member on his work, and then he or she continues on her own work. So processor does other tasks, occasionally interrupted by input output data transfer. It pauses its work, solves it, solves the issue, and moves on. So that is program input output and interrupt driven input output. But there's a better way more than both of this, which is known as data, sorry, my bad, direct memory access. How come this can be better than both of them? Well, the processor does nothing. The processor creates a direct memory access, and what the input output devices is, they use this to communicate with each other. So input output devices transfer directly to or from memory without processor. This is always the best because if the processor can implement one of this, it doesn't have to do anything. It can deal with its own work. So if he is the team leader, instead of him managing the team, he hires an assistant who manages his team. So this direct memory access is somewhat of an assistant to the processor. So a quick recap on what we have learned. So we learned about a bit about assembly. We learned about assembly instruction types, also known as addressing modes. Then we learned about assembly programming functions, also known as instructions and interrupts. And last but not least, we learned about input output operations, right? So we have talked extensively about the processor, and we talked a little bit about the input output. But what about the relationship between hardware and software? So here we are going to learn all about operating systems, device drivers, BIOS setup, and under BIOS we will learn all about booting, bootstrap, so on and so forth. Then we will learn about the computer system components. So under computer system components, we will learn all about the memory subsystem, input output subsystem, graphic displays, network interface, and they have taught us all about mouse and keyboard, but it's just different types of mouses, different types of keyboards, like ergonomic mouse, gaming mouse, different types of keyboards, which I don't think is necessary because most of us already know about it. If you don't, well, just write some bullshit in your exam paper, everything will be fine. So now let us talk about the operating system. So what's the operating system? Well, a good example is Windows, one of the most shittiest operating systems ever made. But it is the only one that is the most accessible, the one that runs exe files, and the one that I can actually play video games in, which is important for me because if not, I will lose my sanity if I keep on studying. Another very good 100% reliable operating system is known as Linux. And as you all know, Linux has many types of distros. There's so much fun to be had in Linux. Another one we can use is Mac or Apple, which is only for rich posh buggers who really think that having a Mac would make them intellectually superior. Newsflash, you're not. You're just like the rest of us, dumb and stupid. Moving on. So, an operating system. Why do you need an operating system? An operating system essentially acts as a bridge between hardware and software component. It's a bridge that allows us. For instance, if I type the letter Y in the keyboard, how can the computer know to display Y on the screen for me? Well, the operating system does that. It takes the data from the keyboard and it does some shenanigans, and all it does is it displays the Y on the application that it requires. So an operating system usually has a few parts. Here is how the operating system usually sits. So there's the user who interacts with an application. The application interacts with the operating system, and the operating system interacts with the hardware. A user cannot directly talk with the hardware. And I mean, he or she probably can, but it'll be a waste of time. I mean, come on, who would want to do that, right? So, what does an OS do? What's an exam friendly answer? Well, it controls or executes users, user programs, or applications. It makes the computer system easy to use, easy to use, and most importantly, utilize hardware efficiently. So these are the three main parts of an operating system. So let us talk about the types of OS. So there are four main types. There's multi-programming, there's multitasking, there's real time, and there's multiprocessing. So, what's the difference between all of them? Well, multi-programming runs multiple programs. No shit, Sherlock, you might say, but multi-programming is essentially the kind of thing that makes sure that all programs run together efficiently, right? Multitasking is something like this. So a computer is usually half duplex. Think of it like that. So all it does, it switches between tasks so quickly that it seems like it is doing both of them at the same time, right? So that is the multitasking. Multiprocessing is something which most of us have because it uses multiple cores or multiple CPUs at the same time. So as you all know, we have dual core, we have heard of it probably, dual core, quad core, all that stuff, right? So that is what multiprocessing is. And real time is a very specific one because it is expected to give an output within a set amount of time. So real time is essentially the one that is used in car airbags because it has to be quick and it has to be fast and it has to be efficient. It doesn't have to wait for other inputs and so on and so forth. So that's what real time OSs are, right? A guaranteed response within a set time limit. Okay. So now we have learned all about an OS, an operating system. Let us talk about device drivers. Now, I believe most of the tech savvy among you have heard about device drivers. Um, so essentially, device driver is it acts as a translator between OS and specific device. Now, like I said, in your laptop, if you have a keyboard, that is probably already imprinted into the memory. But the mouse pad I'm using right now doesn't have its own specific what implementation into the device's register, nor does it have in the OS. So what I do is I have to download a specific driver to make sure that the OS utilizes this device to its full potential and functionality. So good example for this is pen pad, printers, and so on and so forth. Many devices uses device drivers, and all it is, it acts as a translator between OS and specific devices. So here's how the process works. A device driver, first of all, loads the relevant data when connected. It initializes it, and then it does command processing. And last but not least, it does communication. So you might say, okay, wait a minute. So this is probably good for an output system, but how does it work for an input system? You can't, if you press a key, you can't wait till it load, initialize, and command processing and communication. Well, remember we learned the funny thing about interrupts. So most devices, input devices especially, run on in the interrupt function where it will send a message to the OS and by proxy the processor saying, hey, this is there, what are you going to do with it? And the processor is like, okay, so the user has opened up Paint and they need this specific drawing drawn here in this specific line, and then it'll implement it out, and then it'll go back to doing its own work. So I frankly have never seen this, but have you ever seen anyone use the same processor and draw on one screen while playing video games on another? I do think that it is probably possible, but they will have a hard time doing it, right? So let's talk about what this is. So first of all, it loads the relevant driver of the device. It initiates the hardware. So it'll probably, now if we have a mouse, then it'll initiate the light or the infrared light underneath it so that you can track where it's going, right? So it initializes the hardware. Okay. So usually for output devices, the OS sends commands to device. Now, right now, the OS is sending a command to my display saying, hey, express this or write this down. And what happens is the device driver translates it and it makes sure that the device does it. Now, again, in my laptop, my screen is probably already implemented into the memory. But if I can run external output, if I can run external device, then the device driver will translate that command and make sure that it is displayed, right? So there are a few other things. So along with that, there are a few operations that it does. So device drivers also do interrupt handling, where if a it senses an input or data from device, it interrupts the processor and sends signals to CPU. That is one of its operations, device driver. It also manages data transfer. I believe the words speak for itself. And last but not least, it handles errors. So error handling. For instance, let's say that my mouse pad is not working, then it will sense it, and what it will do is it will be like, oh, wait a minute, it's not working, and it will send to the CPU this message, and the CPU will express to me, hey, your device isn't working. So let's say I connect a mouse and it cannot read the mouse or the cable is damaged, then you may have seen device cannot be recognized, right? So all of these are handled by the device driver. So the device driver is very important. So this is what we have learned right now, all of this hardware and software. You think we are done? Oh no, we're just getting started, baby. So let's move on to one of the very main guys in the processor, basic input output system. So what is a BIOS? Well, it's not software, it's not hardware, it's firmware. So let's say you have your processor over here. There will always be a BIOS chip embedded onto it with a set of instructions, right? So let's say you buy a small Lego box, a box containing Lego, right? You are so excited, you want to open it, but when you open it, you only get bits and pieces everywhere. But along with that, you get a manual, right? A manual that says, hey, fix these parts together, and finally you have, I don't know, maybe it's a bunny. So when you open the box, the very first thing that you notice is this, that tells you how to do, what to do, to check everything, whether all the parts are there. Because usually Lego I don't know whether now they have it, but they used to have like, okay, check whether this bag is there, this bag is there, this bag is there, and in this bag there'll be this many parts, so on and so forth, right? So essentially, this is a manual, a set of instructions that checks whether everything is working as intended. So what does it check? So first up, when you boot up the computer, the BIOS works. So firstly, this is activated, right? So it does something known as power on self test, right? Where it checks whether the essential components of a computer are there. So for instance, it will check whether you have a RAM, it will check whether you have a hard disk or a boot device. So what's a boot device? Well, boot device is usually where the OS is stored, right? It will check whether the CPU, the most main important bit, is working. And funnily enough, it will also check whether your display is working. Why is that? Well, if the display is not working and you're seeing a black screen, you're gonna think that the processor is off. But no, the processor is working, the keys, everything are working, but the display is not working. Hence, if some of one of these is not working, it will give out a signal of beeps. So each device has its own error, beep, message type something. Okay. Okay. So it will check whether all of these are working probably properly. All of these are there, whether the OS is there, so on and so forth. And then what it does is it bootstrap loader is loadable. So what's a bootstrap loader? So it is not Davy Jones. Is it Davy Jones? Bootstrap Bill. Ah, Will Turner's father. It is not Will Turner's father, by the way. Very sorry about that. It is in fact the loader that loads the operating system. So it's essentially the OS loader, operating system loader. So the bootstrap loader is activated and it loads in the operating system. Next, we have the boot, or it'll boot up the system. Then it'll do a BIOS test, a BIOS setup, where now I believe if you have tinkered with a computer or click F2 while you're having something, you can see like it has something called a boot order, where it will say, do you want to activate this first, this first, this second. So it usually is the place where you can set priority of how everything boots together. And I recommend you don't mess with this unless you are actually well versed in all of this. You don't have to have a degree, but you should know what happens when you mess with this stuff. So that is all about the BIOS. And last but not least, we need to talk about computer subsystem, computer system components. So the very first system is the memory subsystem. So the memory subsystem includes primary memory, then there is something called secondary memory, then there is virtual memory, and finally we have memory controller. So primary memory does not only have RAM, it has something called cache or SRAM. So as you know, RAM is something that is random access memory. It's volatile. Volatile means it will only work if the device is on. And it's there. It's the thing that runs most data. But what is cache? What is SRAM? I mean, you have probably heard about cache, right? You probably seen your phone say, okay, clear up cache. What does that mean? Well, I just realized that this is essentially uh, stores frequently accessed data. right? So why doesn't it store frequently accessed data? Well, it reduces workload for the CPU. So there's a question. If this stores frequently accessed data and it reduces workload on the CPU, why do devices tell us clear cache, clear cache? Well, something that we should learn more and more. So secondary memory is something called HDD, hard disk, there is SDD, there is optical drive, there is flash drive, so on and so forth. Secondary memory is like external memory of all of this. What is virtual memory? Well, virtual memory is a technique of using secondary memory for RAM, but it's not like you expect. It's using secondary memory as for RAM extension, but it doesn't implement it and use part of it. No, no, no. Here's what it does. So usually what happens is less used data, so less used cache or less use something from the RAM is stored in the external data, right? So usually in the hard drive, and then it frees up space in the RAM, letting it do more work. So that is what's called as virtual memory. And memory controller manages data flow between CPU and RAM. That's all it does. So it can be used to avoid collisions between those data flows, avoid collisions, and optimize the system. So say you find a way for the memory controller to magically talk in two different pathways. Maybe it does happen, but I'm not sure. Let's say it does not happen and you finally figured it out. You have optimized the memory controller to be much more efficient. So the memory subsystem can itself become a lot more efficient. So that is what the memory controller does. And finally, we have to talk about the pyramid. So forgive my ugly drawing, but this is capacity. And when you go from bottom to top, speed as well as cost per bit increases. So on the topmost, we have the OG registers. Next, we have cache memory or SRAM. Then we have the primary memory and main memory, essentially RAM, but it's also called as DRAM. And finally, we have secondary memory or external memory. So you may have noticed that, let's say you are accessing a file from your computer. You can do it within seconds. Let's say you're accessing a file or copy pasting a file into a hard drive. It takes time. Why? Because although it has high capacity, it can store data for quite a long time. It is very slow. Whereas registers, they can't store data for a long time, but they are very, very fast. So this is something that you should know. So what is DRAM? DRAM is also a volatile memory, meaning it cannot work, it can only work if the device is on. It is like the primary primary RAM, and it is used in graphics cards, which means it's used everywhere, literally. That's it. So with that out of the way, let us now talk about DDR. Okay, DDR. So you may have heard, or if you want to buy a computer, you're like, I want to add some RAM. What RAM do you want? Do you want DDR4 or do you want DDR5? Right? So what does this mean? Well, DDR means double data rate memory, right? So all it does is it does two operations, or not two operations, it is it transfers data twice per clock cycle, and it is improving to this day. Finally, we have static DRAM, static uh, synchronous. Yeah. So it is also kind of a DRAM. Okay, it is not related to this, by the way. It is simply just another RAM. It's something another is just an SDRAM. So the difference between SDRAM is it is more efficient because it works along with the clock cycle. It is more efficient, but it is also more expensive, right? It is very synchronized. It's very good, to be honest. And finally, we have the input output subsystem. So the input output subsystem has input output devices. Oh shit, Sherlock. Peripherals. Peripherals. Oh god, I hate writing. Peripherals. Next we have device controllers. So it's like tiny chips. It's like a tiny chip between in each and every single device that basically holds the device drivers like connection, blah blah blah. It's like a small hardware chip on each device, and there are input output paths where those are communication endpoints. So something like HDMI having its own path, VGA having its own path, USB having its own path, right? So the fourth one is input output bus. So it's essentially like a connection between the port and processor, where this can be used to transfer data to parts of the computer. So I believe you remember when we first learned about buses, there are three buses in address bus, control bus, and memory bus. And input output was mainly connected to the two other guys, where it talks to the main memory and it talks to the CPU. So input output bus is essentially like that. And why bus, you may ask? Well, obviously if it can speak to every single part, it will be better, right? Because usually if a mouse is talking, it will talk to every single part, right? So that's why we use buses. And five, we have input output scheduling and buffering. So it essentially, the OS operating system uh, prioritizes which input output uh, output request will happen first, right? So that is essentially, it prioritizes and it does it bit by bit, because it is best, because you can't do two things at the same time. It is never going to work. Too many cooks spoil the broth. So you have to be very efficient, and computers are nothing if not efficient. Next we have, as we talked about, interrupts and polling. So interrupt is essentially a device uh, interrupting the processor or CPU. CPU deals with it, and CPU moves on. Whereas polling is the processor checks on the device time to time, sees if it needs anything done, and does it, right? So Interrupt happens with active team members, polling happens with less active team members. And it's a pain in the ass. I'm speaking from experience from this very module. If you are listening, fuck you. Anyways, next we have data transfer. They are in charge of the data transfer. They are in charge of device management. They are in charge of error handling. Then they are also in charge of efficiency optimization, right? So last but not least, we have VGA used by older systems. Older systems. Oh, sorry. Yeah, older systems to a modern display. Then we have HDMI, which is widely used all over the world right now. It's HDMI, obviously. And finally, we have network interface. So we learned in DCN network interface. There are network interface cards that allows a device to connect to a network, and so there is Ethernet, and it connects to wired system, and then there is Wi-Fi. So usually we have the RJ45 port in most laptops, in most devices, so that you can connect to LANs, wired, and then there's Wi-Fi. Usually there is a module inside of a laptop that allows it to connect to Wi-Fi. So I believe that is all. Uh, I have actually talked a lot today. I hope that you didn't get overwhelmed. So study hard. I hope you all have a great day. And remember, you are loved. Remember, you are cared for. Remember, you are important. Uh, do not seek a temporary solution. Sorry, yeah, do not seek a permanent solution to a temporary problem, because s- life may be hard, life may be shitty, life may be fucked up. People around you may be shitty, people around may be trash. You may be like me at times saying, "Oh my God, Thanos was right." But humanity is beautiful, and there are always two sides of the coin. And if you see the bad, you will also see the good. And if you see good every single day, be glad that you don't see the bad. And thank you so much. I have my mates. I hope anyone who else is watching this, good luck to every single one of you. And thank you. Have a great day.